Okay. Thank you for the presentation. In fact, I have made many different jobs during the last years. I tried to do mathematics in the same time I visited all the world, trying to pass contract between my university and worldwide universities in different countries. And I would like, first of all, to thank a lot the organizers of this conference for giving me the opportunity to do mathematics again. It's a big challenge for me, but it's a great chance for me to go back in the mathematical world. And I would like to tell that I am very pleased to be here in Saint-Malo, and to say that my family is not from Brittany, but from Normandy. And Frédéric, this morning, you talk about the Mont Saint-Michel, and the only important question is to know if the Mont Saint-Michel is in Brittany or in Normandy. I don't know, maybe we could use the theory of chaos this morning to see if what is the right answer, but okay. To be more serious, just to introduce my talk, I would like to say that in fact, I have worked a lot in a specific area, the representation theory of Lie groups. And this area has highlighted a very interesting set of geometric objects called the co-adjoint orbits. That is, the orbits coming from the action of a Lie group on the dual of its Lie algebra. In particular, when the Lie group is nilpotent, exponential, or solvable, its unitary dual, that is the set of irreducible unitary representations, has been parameterized by the set of co-adjoint orbits, using what we call the orbit method. And this method has been developed by many authors, mainly three authors at the beginning: Kirillov, Constant, and Bernat. And what is, for me, very nice in this method is that we try to make a correspondence between the set of these representations and the set of orbits. It's a way to make the correspondence between the two sets. And the extension of the orbit method to semi-simple groups, one then considered after exponential, solvable, and nilpotent groups. We have considered the case of semi-simple groups, and answers have been provided by many authors. I will say Constant first, David Vaughan, Michel Duflo, and many others. And the extension has used the geometric properties of such orbits. The main part of my mathematician work has been dedicated to that specific area, and more precisely to the role played by the nilpotent orbits in the description of the unitary dual. And that approach has conducted to consider another nice property of co-adjoint orbits. They are indeed symplectic leaves of the Lie Poisson structure of the Lie algebra, which leads to study how locally the Poisson manifold, the Poisson structure, can be described using the symplectic leaf and using another structure. We will call it the transverse Poisson structure. And what I will try to show you is that for specific orbits, that is the subregular orbit, we get very nice results in terms of geometry of the Poisson manifold. That I will try to explain today. So the title of my talk, you will see it. It's coming from the talk is coming from a paper you will see there from Paul Van Ecke, myself, and Pantelis Damianou. And if you don't mind, I would like to dedicate my talk to Pantelis, who was a very good friend and who passed away 2 years ago. Okay, so first of all, I would like to introduce, I think that everything I will present is elementary. I will try to do very elementary mathematics. You will see it's not very hard. So the first thing I will try to introduce is the notion of transverse Poisson structure. So the transverse Poisson structure was introduced first by Alan Weinstein in his famous splitting theorem, stating that any Poisson manifold M is locally in the neighborhood of each point M the product of the symplectic leaf and of a submanifold N, such that you have this equality in terms of tangent spaces. That means that there is a neighborhood V of M in N, a neighborhood U of M in S, such that the Poisson manifold M is the product of these two spaces. And what is very, very important is that you can endow the Poisson submanifold, I mean V with a Poisson structure. And we'll call the submanifold N a transverse slice to the symplectic leaf S, and we'll call the Poisson structure defined on V the transverse Poisson structure to S. That's the general situation. Now we'll look at a specific example. We look at the example of Lie algebra. So, if now we consider a Lie algebra G and its dual G star, we can equip this dual with the standard Lie Poisson structure defined as follows. Let mu in G star. We will use very natural identifications between G star and the tangent space of G star at mu, and then between G and the cotangent space of G star at mu. And so, with these identifications, you can consider the differentials of any function on G star as elements of G. And that can give you there the definition of a Lie Poisson structure on G star. You take two functions on G star, and the Poisson bracket of f and g at mu is mu of the Lie bracket of d mu of f, d mu on g. And what is very interesting is that if you consider x and y as particular elements of G, you have a correspondence between the Poisson bracket of x and y and the Lie bracket of x and y. And the last very important fact is that in that situation, the symplectic leaf through mu is exactly the coadjoint orbit G of mu, where G is the adjoint Lie group. Okay. I will just mention the semi-simple case because it is the case I will consider for the rest of my talk. Oh, sorry, it's above. So if G is semi-simple, maybe you know that we can identify G and its dual via the Killing form, K, and the Lie Poisson structure on G is then given by this formula, the Poisson bracket of f and g is k of x and the Lie bracket of the corresponding differentials. And you have this formula we will use in the rest of the talk. That's the notion of transverse structure. And now we will go to the transverse Poisson structure. I will, at the beginning of my talk, I will tell you that I have told you that the transverse structure is endowed with a Poisson structure, but how can we calculate this Poisson structure? You will see that, in fact, the calculation is very, very simple. For me, it's very simple. So we keep the same notation, G star, G and mu in G star, and we introduce the centralizer of mu in G of mu. A natural transverse slice to the orbit J mu is obtained in the following way. You choose any complement as a vector space, any complement n of j of mu in G. And we consider the affine space, n mu is mu plus n orthogonal, where n orthogonal is defined as follows. It's the usual definition. And it is very simple to check that the orthogonal of J of mu is exactly ad star of G of mu, which is the tangent space of the orbit at mu. And then you have this equality. And this equality shows that the space n mu I have introduced is a transverse slice to G mu, and of course we have that property that the dimension of n mu is the dimension of G minus the dimension of a G orbit. That's the situation we'll consider now. And to calculate the Poisson structure on N, I will restrict my talk to the semi-simple case. I can do the same for general case, but I prefer to consider the semi-simple case. So we use the Killing form K. And I introduce any element E of G, the composition G equal G of E plus N, as before, and I choose basis of G. So I define a basis of G by a basis of G of E and a basis of N, without any restriction about the basis. It's a very general choice, yes. And after this, having introduced this basis, I consider this linear coordinates centered at E. Qi of y is k is the Killing form of y minus E zi, and qi plus k of y is k y minus E xi. It's very easy to see that you have this property, but it's not useful. And you introduce three matrices, C, B, and A, by the following formula. Okay? C, you consider the Lie bracket of XL and XM, so you are here in N, but don't forget that the Lie bracket of two elements of N is not necessary in N. N is not a subalgebra. And for B, you have that. And for A, you have that. And if you look at the formula, you will see very easily that the entries of B and A are linear in the coordinates, and not for C. So it's not linear, it's affine. And it is very easy. It's a problem that a master student could solve, that the matrix C of E is invertible. Then, because this matrix is invertible, you can say that C of Y is invertible in a neighborhood of E in the transverse slice. Okay? So you have two matrices, E and B, and one which is invertible. Okay? And the Poisson matrix of the Lie Poisson structure is then given by this matrix A, B, C, and minus transpose of B. This is the general formula of the Lie Poisson structure on G. And we use a special techniques called the Dirac reduction to extract the Poisson matrix of the transverse Poisson structure on N. And in the coordinates Q1, Qk, this transverse Poisson structure is given by this formula. Lambda of N is A of N plus B of N transpose C on N minus 1, B of N. The first remark we can do about this formula is the following. If you remember how you compute the inverse of the matrix, you have to divide by the determinant. So all the coefficients of this matrix are rational functions in Q1, Qk. It's very easy to see. And so the question, we have tried to, oh, sorry. What is the problem? Okay, that's okay. Merci. And so the question we have considered with Paul Vaneke and Pantelis Damianou is a multiple question. The question is the following: for which Lie algebras, for which orbits, for which complements is the Poisson structure polynomial? Because you know it's easier to use polynomial, objects than rational to compute many things. That's the question we have tried to solve. It is not a millennium problem, okay? I will not aim $1 million for that, but it is interesting question for many reasons. And that leads us to consider a specific way to define the transverse Poisson structure using the semi-simple theory of Lie algebras. The first remark is that the only orbits which count are the nilpotent orbits, and not all the orbits. Why? Because I will start using specific semi-simple machinery. The first theorem I will use is due to Jordan-Chevalet. It's a Jordan-Chevalet theorem, which says that any element x of J can be decomposed as x equal S plus E, where S is semi-simple, E nilpotent, and when the bracket of S on E and E is 0, which leads to say that the centralizer of X in G, G of X, is the intersection of G of S and G of E. And what we have proved with Pantelis and Paul is that, in fact, the transverse Poisson structure on G of X reduces to the transverse Poisson structure of its nilpotent part with another group, but we reduce to the nilpotent part. And the proposition is the following. So let's any X any element of G, the X equal S plus E, it's Jordan-Chevalier decomposition. So we consider any complement NE of G of X in G of S, and we put N equal to NE plus NS, where NS is the orthogonal of G of S. So we have NE and N. Then NS, I told, is the orthogonal of G of S. Yes. Then the two affine spaces, capital NX and capital N. Capital N is defined from X, and capital N is defined from E. These two affine spaces are parallel, and they are respectively transverse slices to the adjoint orbit Jx in G and to the nilpotent orbit J of SE in G of S. So you have this correspondence between one orbit in G and one nilpotent orbit in G of S. And what is very remarkable is that the Poisson structure on both transverse slices has the same Poisson matrix in the same coordinates restricted to the corresponding slice. In fact, the only thing we have to study now is not all the coadjoint orbits, but only the nilpotent orbits. Okay, that's the first step. Then, let me introduce another notion, which is, I think, very well known, is the notion of quasi-homogeneous polynomial. You have here the definition. A polynomial in d variables x1, xd is said to be quasi-homogeneous relatively to non-negative integers nu1, nu-d, if for some integer k of p, you have this equality there. Okay, so p, t mu1, x1, etc. is t power k of p, p, x1, xd. And if you have that, the k of p is called the quasi-degree of the polynomial. So you introduce for this polynomial a notion of quasi-degree. And a Poisson structure is said to be quasi-homogeneous if there exists a k such that for any fg quasi-homogeneous polynomials, their Poisson bracket fg is quasi-homogeneous of degree k of fg equal to k of f plus k of j plus k. And this k is called the quasi-degree of the Poisson structure, of the bracket. Okay? And now I have to go further in the techniques in semi-simple Lie algebras. Before, I told you that I could choose any complement n for the centralizer of mu. Now I will try to precise for which complements I will get the right property of, that is that the Poisson structure is polynomial. And I will introduce the notion of Cartan subalgebra. So I choose a Cartan subalgebra H of G. If you don't know I don't know, maybe you are. If you don't know this notion, you have to think about the case of SLN and the diagonal matrices. It's Cartan subalgebra. And I introduce the delta, the corresponding root system, and pi, which is the basis of simple roots, and O is in the important orbit. I will use this correspondence, Jacobson-Morozov constant, which is very, very, very important in the theory of semi-simple Lie groups and Lie algebras. It's a way to describe an orbit in terms of elements of the Lie algebra, in terms of what we will call the SL2 triple. More precisely, there is a triple HEF associated with the orbit O, and, what is very important, completely determined up to conjugation by G of H by the following properties, 3 properties. The first is that the triple HEF is a SL2 triple. That is, what is a SL2 triple? It is a triple where H is semi-simple, EF nilpotent, and where you have these properties. The bracket of H and E is 2E, H and F is minus 2F, and E and F is H. That's the first property. The second is that H is what we call the characteristic of the orbit. What is a characteristic? It is an element of H satisfying that property that alpha of H is 0, 1, or 2 for any root alpha in pi. And the third property is that the orbit is generated by E. Okay, so I introduce this correspondence. We will do everything for the rest of my talk. And then I will introduce also 2 decompositions of the Lie algebra. For that, I will introduce the subalgebra of G isomorphic to SL2 of C and generated by HEF. So this the Lie algebra can be decomposed in eigenspaces relatively to add H, and we know that each eigenvalue is an integer, such that we have this decomposition. G is the direction of G of I, where I is in Z. And the second decomposition is a decomposition of G as a simple, in simple modules. Of course, the subalgebra S acts on G, and so we have this decomposition. G is the direction of V and K, where each nk is the highest weight of the simple S module V and K. We can easily see that the dimension of V and K is nk plus 1. And then you have all the weights appearing in the decomposition, nk minus 2, minus 4, etc. So you have a very, very precise description of each simple S module. And now, that's the important part of my talk, one of the important parts of my talk. I will introduce the set of add H invariant complements. So I restrict the set of the complements. Now I choose only the add H invariant complements of G in J. And I build the previous basis of G. We call that ZI, the ZI were the elements of the G of E. So now we choose each ZI as the highest weight vector of weight and I. There is a very simple fact saying that the G of E is defined by all the highest weight vectors of that decomposition. And each xi is a weight vector of weight nu I. So you take, in fact, the highest weight vectors, and after you consider all the other weight vectors not chosen in G of E. You see, it's very elementary. Very elementary. And then you define, as done before, the corresponding linear coordinates, Q1, Qk. And I build, using the Dirac reduction, I build the transverse Poisson structure. This structure, built, as I told you, is called adjoint transverse Poisson structure, or ATP structure, attached to the orbit. And the first theorem we prove with Pantelis and Paul is the following. First, the ATP structure on N is polynomial, so all the entries of the Poisson matrix of this structure are polynomial in the coordinates Q1, Qk. And the second result is that the ATP structure is not only polynomial, it is also quasi-homogeneous polynomial of quasi-degree -2. It's always -2 for any orbit. Relatively to the quasi-degree n1 plus 2, nk plus 2. So you have here the highest weights defined before. And so we have a first answer to the question I have asked before. For a certain set of complements, a certain choice of the basis, we have the right answer. And just to have a look on a very simple example, I took the example of SL4. Maybe you know that all the nilpotent orbits of SLN are parameterized by partitions of n. So for SL4 you have, as partitions you have 4, 3, 1, 2, 2, and 1, 1, 1. 4 is a regular orbit. I will not consider that case. And I consider the partition 3, 1. In fact, it is the subregular orbit. And here you have the description of the situation in terms of world system and so on. And then you have the calculation of the transverse Poisson structure in terms of very simple polynomials. Okay. I will add now for the rest of my talk to consider only the sub-regular case, and to show you that in that case we have very nice results about the geometric properties of the Poisson transverse structure. First of all, I would like to recall some basic facts about orbits. If O is any orbit in G, L the rank on G, it is very easy to see that the rank of the ATP structure, I mean, when I'm talking about the rank of a Poisson structure, I'm talking about the rank of a matrix, the generic rank of a matrix. And the fact is that this rank is very simple. It's dimension of G minus the rank minus the dimension of O. If you look at the big nilpotent orbit, what we call the regular orbit, the maximal orbit, we know that the dimension of the regular orbit is dimension of G minus L. If you replace there, you find that the rank of this of the transverse structure is 0. So it's not interesting. And so the first interesting orbit is to consider is the subregular, which is the orbit below the regular. And I recall that for that orbit, the dimension is dimension of G minus L minus 2. Of course, I take the previous notation that is OSR is GE, where HEF is the canonical SL2 triple associated to the orbit. And then you have that the dimension of G of E is L plus 2. It is also the dimension of the transverse slice. Okay. I use now a very classical result, an old result of the Claude Chevalet. Claude Chevalet described completely the algebra of Aj invariant polynomial on the Lie algebra J. And this Lie algebra, that algebra, is in fact generated by L. L is the rank of the Lie algebra. L homogeneous polynomial, G1, GL, whose degree, the degree of GI, is di equal to mi plus 1, where mi is what we call the exponent of G. So it is very interesting to use these polynomials. And it's also very simple to check that by G invariance, these polynomials are in fact the Casimirs of the Lie Poisson structure. That's the first fact. The second fact is we consider the map G from the Lie algebra to C power L, defined by G of X is G1 of X, GL of X. And we look at the fiber in 0 of this map. And what we find is that this fiber is exactly the nilpotent variety N of G. So we introduce this nilpotent variety. Okay. Now we will restrict that situation to the transverse slice. So we restrict all the G1, GL to the transverse slice. And so we consider the restriction, Chi1, Chi-L, which are L independent Casimirs on the ATP structure. So we have L independent Casimirs on the ATP structure. And we call that N, in the case of the subregular, the dimension is L plus 2. So we have a very interesting description of a great part of N using the Casimirs. Okay, and what we can prove also is that each chi is a quasi-homogeneous polynomial of quasi-degree 2di relatively to the same weights coming from the highest waves. Okay, now I have, okay, it's okay. It is not the chaos. I will introduce very quickly the notion of simple singularities. I will recall what. Okay. We call very well-known facts about simple singularities. Up to conjugacy, we know that, in fact, there are 5 types of finite subgroup of SL2 of C. This one, cyclic, dihedral, tetrahedral, octahedral, and icosahedral. And we consider for each such subgroup, F, we consider the ring of invariant polynomials in 2 variables, U and V, invariant by Herve. And what we know, it's something which has been precised by Slodowy, is that this polynomial, this ring, excuse me, is in fact generated by 3 polynomials, x, y, and z. And these 3 polynomials are satisfying one polynomial relation R of x, y, z equal to 0. That's a very interesting fact. And the quotient space C2 over F can be identified as an affine space with the singular surface R equal to 0. C2 over F is identified to that surface, and the origin is the only singular point. So it is a surface with only singular point. And we call it an homogeneous simple singularity. What's the relation between this notion of singularity and the theory of Lie algebra? Here. Because now we consider a resolution, the minimal resolution of C2 over F, we denote it by pi and x, and we know that the minimal resolution of that has an exceptional set, which is defined by that, which consists of projective lines. So we introduce projective lines. And what is remarkable is that the intersection pattern of these lines forms a graph, which is that of one of the simply laced Dynkin diagrams of type ADE. So from the notion of homogeneous simple singularity, you extract, in fact, Dynkin diagrams corresponding to these 3 types, ADE, and so corresponding to Lie algebras. We can define in a similar way, I will not define precisely, but we can define in a similar way inhomogeneous simple singularities, and we get in a similar process the other types of Dynkin diagrams, namely B, C, F4, and G2. And the very important, very nice result due to Slodowy is the following. I mean, maybe. So let G be a simple complex Lie algebra with Dynkin diagram. I forgot to tell you that the type of the diagram is called the type of the singularity. Okay. And so let J be a simple and complex Lie algebra with a Dynkin diagram of type delta. If we consider the subregular orbit, OSR, and its transverse line N, and if we consider the surface, which is the fiber in 0, of the Chevalier map, so chi minus 1 of 0 equal to the intersection of the nilpotent variety and the transverse lines, and then this surface has a simple singularity of the type delta, And so for the subregular, you have this connection between simple singularity and the notion of Lie algebra. Here is a very simple example of the situation. You consider the subregular orbit of SL4. You calculate the 3 Casimirs of the ATP structure for this orbit there in the coordinates Q1, Q2, Q3, Q4. And you express the 3rd Casimir in terms of the others, and what appears in that equation. And what we find is that polynomial is the equation of surface, which corresponds exactly to the simple singularity of type A3. So you check that this proposition is exactly true in that case. Okay? I will finish, I think, yes, it's okay. I can finish in 5 minutes or 10 minutes. I will finish by another interesting property of the subregular orbits, which lead to the second theorem we prove with Pantelis and Paul. We call that for subregular orbit, we have the ATP structure is of rank 2. There is another Poisson structure which can be defined on the transverse line N using the Casimirs. And it is called the determinantal structure or the number structure. I will call very briefly how it is built. It's also very elementary. You consider d-2 independent polynomials in d variable x1, xd. You take the nabla f, which is the differential of the function f, which can be expressed as a column vector with the partial differential of f. And we define a Poisson structure, which is called the determinantal structure, by these brackets. So the bracket det of f and g, which are polynomials, is the determinant of nabla f, nabla g, and nabla of each Casimir. So we prove, so it's very easy to prove that it is a Poisson structure, and that the rank of the structure is 2. And moreover, if the pi are quasi-homogeneous, it is simple to check that the Poisson bracket det is also quasi-homogeneous. Of course, if we take f and g quasi-homogeneous polynomials. So now we have 2 structures: the ATP structure for the subregular orbit and the determinantal structure. We have 2 structures, Poisson structures. We know that the 2 structures are both of rank 2, and they have the same independent Casimirs. I forgot to tell you that, of course, I will use this construction to using the chi1, chi-L, of course. And so we have the ATP structure and the determinantal structure using the Casimirs chi1, chi-L. And the theorem we prove with Pantelis and Paul is that, in fact, in the right situation, so with the notations introduced before, the two structures, so the ATP and the determinantal structure, differ only by constant. And I will finish maybe by a very, very quick sketch of the proof, because you will see that the proof, in fact, uses all the things introduced before. First of all, if we consider the matrices of the two Poisson brackets, we consider them as coefficients in the field of rational functions on x1, xd. We see that these two matrices act as Q-symmetric endomorphisms on Rd, that the two matrices are of rank 2 and have the same kernel. So it turns out that there is a rational function in R such that the two Poisson brackets differ from this rational function. And the second part of the proof says that if the denominator Q is not trivial, then if you then Q has to divide all the coefficients of the matrix, because we know that the matrix, that the Poisson structure are polynomial. And so that means that the fiber has to be singular, not only on one point, but on a surface. And that leads to a contradiction, because we know that the singularity is simple. That here that we use the notion of simple singularity. And then we find that Q is trivial, and P is in fact constant due to the calculation on the quasi-degree. And to finish, 10 seconds. If you consider the subradial orbit of SL4, we compute the determinant structure using the Casimirs I have introduced before, and what we obtain in that, and it is, if you look at the previous matrix introduced before, you see that the constant is 192. So it's very simple to see that you have exactly this result. Thank you. Just to finish my talk, I would like to tell you that we have studied only one case, the subregular orbit. And so I think that this area can be very rich in terms of results, because we could imagine to look at the other orbits. The only problem is that if you reduce the dimension of the orbit, you increase the rank of the ATP structure. So the calculations are probably more complicated. But I think it could be interesting to try to have a general description in terms of geometry of this transverse structure. And my last idea, I told you before, is to try to link the geometry of the transverse Poisson structure to the unitary dual of Lie groups. I am sure that there is a very precise, very interesting link, but I have not yet found exactly. I have not found the good idea. So thank you very much.
So before one or two questions, I just want to motivate the community of GSI to look at these structures. So if you are interested in information geometry, in fact, so it appears not if you are working on a Euclidean space, but if you extend, like Souriau for Lie group, the structure of information geometry, you have a foliation, which are given by symplectic foliation, which are given by the coadjoint orbit of the group. And you have a Casimir function, and this Casimir function, which is constant on the symplectic leaf, is the entropy. Okay, so it is also a very full meaning for thermodynamic, because the entropy, you have a geometric definition, is a Casimir function on the coadjoint orbit. And what does it describe? It describes non-dissipative phenomena, because you have constant entropy. And what is interesting is the transverse structures, and the transverse structures describes dissipative thermodynamic. Mm-hmm. So all the dissipative thermodynamic is described by these transverse structures. So it could be interesting for information geometry of deep learning. For the time being, you are using a gradient algorithm, which is a non-dissipative gradient. And what does it mean to make learning with dissipative structures? So it's, I invite you to explore coadjoint orbit, which is a very rich structures, and especially also the transverse Poisson structure. So do you have one or two questions? Yes. Short.
Of course, the coadjoint orbits are symplectic manifolds, but there are some special ones, such as Kähler manifolds that occur from the highest weight representations. They're interesting to you, or they are too regular?
Excuse me, I have not.
So the highest weight,
yes.
Highest weight vectors, the orbits going through highest weight vectors, have the additional property of not just being symplectic, but being Kählerian.
Yeah.
But are they too regular? A lot of orbits are Kählerian.
No, I don't. Yeah, there is a lot of properties about IOS rate, but I used only the definition of the IOS rate. But I think we can go further. Oh, sorry, and use the very precise properties about this decomposition.
Because these Kählerian orbits, of course, have holomorphic representations.
Yeah, exactly.
Hi. Thank you for the presentation. I have two short questions. First one is regarding the two slides. You used the letter F. I didn't get what F is. So on your first slide, I think it was can't manage. If you go backwards, please. And the second question is F exactly. And the second question is, can we align somehow Quiver representations and moduli space of Quiver representations in that framework? And is that also something which is promising for information geometry?
No, I told you that for the representation of Lie groups, you are talking about representation of Lie groups.
So you're just for Quiver representations, the moduli space of Quiver representations, where we have the Quiver of the Lincoln diagrams, and the results are very similar, and we also have the nilpotent orbits. So I was just curious whether this can be applied to information geometry.
Okay, no, I cannot tell you about that, but if you read about the paper of Slodowey, you have many information about this link between the Deakin diagram and the singularities. But we can discuss after, but it will take a long time. It's very, in fact, it's very, very precise. So we can really build the diagram from the situation, but it takes a long time. For the first question, I don't remember the F. What is the F? Huh? Ouais.
The second slide, not the first slide.
Yes.
Is the intro, is the title. Okay.
Okay. F,
at the bottom. So.
Bottom.
So here, let Fg from Fg star. I really don't get it.
Okay. It's the set of function on G star.
The set of functions. Okay.
I'm sorry. Yes.
Is there a connection with NAM equations? Because complex semi-simple coadjoint orbit are not only Kähler but hyperkähler, and the constructions go through NAM equations, which is a very interesting dynamical system. So is your transverse Poisson structure, a kind of, I don't know, slides of, I don't know. Can you relate it to a dynamical system on your?
Maybe, maybe. I think it's this question has been for me. Somebody asked me this question coming from the resolution of Hamiltonian equations. So of course there is a very interesting relation between this problem of transverse structure and the notion of integrable systems. We have some results about that, but I cannot go further. I don't know.
Is there links with work of Picard?
No, the work of Van Mobeck and Van Eyck.
Okay. Thank you very much.
About integral systems. Yeah.
Just one last question. In information geometry, the transverse foliation will be a metric foliation. It makes sense in your structure, the particular case where you have a metric foliation for the transverse structure?
No, I think it's a very smart question.
Okay.
I have not thought about that, but I think it could be interesting to think about the notion of metrics to put on the transverse structure. Yes. Okay. Yeah, it's a good idea for continuing the work.
Okay. Thank you to Professor Sabourin.